you.
So yes, thank you all for being here, and thank you, Stefania, for setting this up. It's very, very nice to be here to present my work. So yes, today I wanted to talk about a paper that I've worked on with some collaborators a few months ago. So Wen Yuan Ai from King's College London and Jorinde van de Vis from Utrecht University. So yes, here we are looking at first order phase transition during the early universe, and more specifically, we're trying to compute the bubble wall velocity. So if you're not familiar with that, I will talk a bit about what all of these things are in a bit. And yes, another thing that we want to do in this paper, which is more new, in fact, is to do it in local thermal equilibrium. So this is an approximation, but we will see that it helps us a lot to simplify a lot all the equation that we will get at the end. So yeah, this is not working anymore. Yeah, I can just. Yeah, it's not working anymore. Okay, thanks. So yes, this is the outline of the talk. So like I said, I will begin with a brief description of first order phase transition. Then I will go to how we can compute the wall velocity in a more general framework. So here in the second part, I won't assume LTE just yet, local thermal equilibrium. It's only in the third part that I will do that and find model-independent fluid equation that will be much more simple than what we get in the second part. And finally, I will discuss some of our results. So yes, basically to get first order phase transition in the early universe, what we need, the starting point of that discussion is usually some scalar field, which depends on some potential like we see here. And the thing that is special with this potential here is that we need two minima that coexist at the same temperature, and they need to be distinct so that they are separated by a potential barrier. And basically what we need is that the relative depth of these two minima to change with the temperature, such that at very high temperature, we see that here the real minimum, the global one of the potential, is at the origin. So we can assume that the scalar field will start at the origin where it is energetically favored. And then at some temperature that we call the critical temperature, the two minima actually become degenerate, so they have the same potential energy. And below that critical temperature, it's actually, the situation is inverted. So the second one, the one on the right, becomes the true minimum, which is energetically favored. And it's possible now to get a phase transition at that point, below the critical temperature. So yes, in general, the phase transition will not happen right at the critical temperature, simply because there is a potential barrier that it needs to go through. And this can be done via two mechanisms, either quantum tunneling or thermal fluctuation if we are in a thermal bath. And usually this is the latter that will be dominant. And yes, usually I will show how we can compute the nucleation temperature at which the real phase transition will actually happen, but this is always smaller than the critical temperature. So yes, to compute the tunneling temperature, the one at which the phase transition happen, we need to compute this tunneling rate here. So this depends on the S3 action, which is essentially the action of the field profile that optimize the tunneling from one vacuum to the other. And so to determine that, we need to solve this equation of motion here for the scalar field. And yes, basically, for the phase transition to happen, we want roughly one bubble to be nucleated per Hubble volume. And this will happen when this gamma rate here is roughly of order of the Hubble rate. So this is how we can compute the nucleation temperature. And basically the phase transition will happen something like that here. So because there is a potential barrier between the two vacuum, it cannot happen homogeneously throughout the whole universe at once. It will first start in a very small region of the universe that we call a bubble, which are these small red circles here. So inside this bubble, we have the new phase where the scalar field has acquired a vev, and outside we still have the old one. And these bubbles will expand until they collide with one another and fill the whole universe. And so this red line actually is the boundary between the old and new phase. And this is what we call the bubble wall. And what I will be trying to do in this talk is to compute the velocity of this bubble wall. So at what speed does the bubble expand, essentially. And so, why are we actually interested in first order phase transition? There are a couple of reasons for that, mainly because they are quite violent event in the early universe, so they can leave some very strong signals that we could hope to observe one day. The first one of these signals would be the ability to do baryogenesis with one of these phase transition. Basically, we know that we have some net baryon asymmetry in the universe that the standard model is not able to generate on its own. So we need some new physics to explain that asymmetry. And first order phase transition would be one of the one mechanism to do that. So yes, basically what it does for us is that it provides one of the three Sakharov conditions. So in any baryogenesis scenario, we need three conditions to be satisfied. So there's B violation, CP violation, and departure from equilibrium. And this is the third one that first order phase transition does for us. Basically, around the bubble wall, the masses of the particles vary very rapidly, and that drives the plasma out of equilibrium. So this is how we can do baryogenesis with that. And one mechanism to do that is electroweak baryogenesis, where we use the electroweak phase transition to generate this baryon asymmetry. And then, of course, something that has been very popular in the last few years is gravitational wave production from first order phase transition. So basically, when the bubbles collide with one another, they create sound waves in the plasma. And these sound waves, when they dissipate, they will create gravitational waves that we can hope to observe in not too long. Actually, in 10 years, there will be the space-based experiment, LISA, that is supposed to be launched. And this is the first one that we can actually hope to see these gravitational waves. So this is very exciting. And yes, because of that, there has been a lot of research done towards the gravitational wave produced during this phase transition. So yes, now I will talk a bit about how we can compute the wall velocity. And just before I do that, why is it important actually to know the wall velocity? And this is actually related to the two signals that we can produce. So we see that in both cases for the baryon asymmetry produced, it depends quite sensitively on the wall velocity. So this is the baryon asymmetry that we produce as a fraction of the observed one. And this is using two different methods to compute the final asymmetry. And in both cases, we see that it's actually quite important to know the wall velocity to have a precise prediction. And on the right-hand side, we have the prediction for this kappa factor here, which is essentially the ratio of energy which will be dissipated as sound waves after the phase transition. And so to have a large gravitational wave spectrum, we want this kappa to be as high as possible. And again, we see that it depends a lot on the wall velocity. So that's why we really need to know quite precisely what the wall velocity is, or at least have a basic idea of what it is.
May I ask you a question?
Yeah, sure.
Is the gravity that you have around the 35, zero.
You're talking about this one?
Yeah.
Oh yeah.
And because everything is okay, but it's not line. Makes sense.
Yeah. In fact, since this paper, there has been some other studies. Yeah, and in fact, the VIA one, the blue one, it has been shown that it's not correct anymore.
So it's the blue one, which.
Yeah, the blue one is not correct.
But this is what I was thinking. If you have such an effect, you should have also a physical understanding of why, for a specific velocity, you don't produce basically any baryon asymmetry.
You're talking about this?
Yeah, I'm talking
okay.
about that. It's surprising that for a specific velocity, you don't produce.
Yeah, that's right. In fact, it's because the final asymmetry is a sum of different contributions, and sometimes they can cancel one another. And that can happen at some very precise velocity like we see here.
Okay,
and
thank you.
Yeah, that's pretty much what. But yeah, this calculation is also very uncertain. So I wouldn't, yeah, this value of the zero is not necessarily very well understood there. Yeah, so yeah, that would be something that we should look at in the future, I think. Yeah. So now, how can we actually compute this wall velocity? The first thing we can do actually is just require that the energy momentum tensor is conserved in the plasma. So this is some very basic physics. We just need to include all the contribution that act in the phase transition. So we have, of course, the contribution from the scalar field, which is just the usual energy momentum tensor for scalar field. And of course, you have also some contribution from the plasma, where we have to sum over all the distribution function of all the species in the plasma. And yes, in general, we don't know beforehand what is this distribution function, simply because, like I said before, the wall will disturb the plasma and it can drive it out of equilibrium. So in principle, f, the distribution function, it's something that we have to compute. We can guess that it will be close to equilibrium if the effect of the wall is not too strong. So typically what we do now is that we will expand this f into an equilibrium part plus some deviation from equilibrium delta f. And the equilibrium part is simply the usual Fermi-Dirac or Bose-Einstein distributions. But here, something special that we do is that we allow the temperature and plasma velocity to depend on the position inside of the wall. This is quite important because at the end, we will want to linearize in delta f. So we want delta f to be as small as possible. And by allowing the temperature and plasma velocity to depend on the position inside the wall, the equilibrium part will fit more closely the real distribution function, and delta f will be smaller. And actually, for most species, delta f will actually be zero. All the species that are not driven out of equilibrium because they don't acquire mass during the phase transition, like all the leptons or the lighter quarks, they will have a delta f of 0, so that will be much simpler to describe at this point. And yes, at the end, we can substitute this NZAT into the plasma energy momentum tensor. And the first two terms are the part for the equilibrium distribution function, which is simply the usual energy momentum tensor for perfect fluid. And then we have some contribution from out of equilibrium effect, which is just this integral here, where we replace f by delta f. And so now what we can do is to assume that the bubble wall, the region where the scalar field actually varies, we will assume that this region is very thin compared to the bubble radius. So this is a good approximation if we wait long enough so that the bubble has become of Hubble size, roughly. And in that case, we can assume the wall not to be spherical, but just planar, because the curvature has become very small. And in that case, we can already integrate the two equations that we got from conservation of energy momentum tensor. And we get these two matching equations, basically that relate these two thermodynamic quantities on both sides of the wall. So basically what it tells us is that very far in front and very far behind the wall, these two quantities must be equal to one another. And this is very interesting because these equations are actually much simpler than the energy momentum tensor that we had on the last slide. For example, they don't depend on delta F, the out of equilibrium distribution function. And this is not because we assume equilibrium yet. We haven't done that yet. It's just because far from the wall, we know that all the deviation from equilibrium should go to 0 so that we recover a plasma in equilibrium. So delta F is actually 0 when we are looking very far from the wall. Also, we see that it doesn't depend on the scalar field, simply again, because far from the wall, we know that the scalar field should be on the true or false minimum. So it actually becomes a function of the temperature. And so we get two equations that depends only on the plasma velocity and the temperature of the plasma on both sides of the wall. So this is four quantities plus the wall velocity, which is a fifth quantity. Yes?
So for this chemical explanation, right, we have to so for this thin wall approximation, do you have to assume some kind of supercooling so the wall becomes big enough before percolation, or it doesn't matter?
Yeah, I don't think we have to assume anything like that. Basically, at the end of the phase transition, we expect to have a couple of bubbles for each Hubble volume, between 1 and 100 usually. And so in every case that we can think of, this is the bubble radius will be much larger than the thickness of the wall. So in that case, it's a good approximation to just say that it's very thin. It's actually, we treat it as a discontinuity actually. And so because of that, we can assume the wall to be planar. Yeah.
Oh, okay, but I mean, if I get beta over h of something like 10 to the 5, then does it still work, or is it too small?
Oh, yeah, at some point, yeah, it could be a problem, but yeah, I've not looked into that precisely, but I think the bubble thickness is actually like orders of magnitude below the Hubble rate. So I don't think it would be a problem, or at least we would have to have a beta factor huge, which would be very hard to get probably. And the gravitational wave and baryogenesis that we would get from that wouldn't be very interesting. So yeah, it's possible that what you say is true for very high beta factor, but in general, this is a good approximation.
Okay. Okay.
So yes, basically we have two equations here that depends on the temperature and plasma velocity on both sides of the wall, plus the wall velocity. So this is 5 parameters. In addition, we also have always two boundary conditions. So for example, in the simplest case for detonation, B plus and T plus, the quantities in front of the wall, are unperturbed, so the plasma is not perturbed by the wall in front of it. So B plus will just be equal to the wall velocity and T plus to the nucleation temperature. So at the end, we only need to recover 3 unknown parameters, but we have 2 equations to do that. So of course, we need one other equation. but it's still possible to derive some useful to know a couple of things about the dynamic of the phase transition just by assuming a fixed wall velocity, not solving the whole system, but solving a subsystem when we assume that we know the wall velocity. And basically, we can show that there are three types of solution that we can get. The first one is a deflagration. So this is a subsonic solution. So simply, this means that the wall velocity is smaller than the speed of sound. And for this solution, the plasma behind the wall will be at rest. And in front of it, there will be a shock wave propagating from the wall, which is here, to the speed of sound, essentially. Or there could be a shock front to after the speed of sound. Then we also have detonation, which is essentially the opposite. So this is a supersonic solution. The plasma in front of it is at rest, but behind it, there is a rarefaction wave that propagates. And here, actually, the smallest velocity that we can have for detonation is called the Jouguet velocity. And the Jouguet velocity is always greater than the speed of sound, so that detonation are always supersonic. So this means that between this, the speed of sound CS and the Jouguet velocity, there's still a gap that we don't have any kind of solution. And this is where we have a hybrid solution, which is really a mix of the latter two. Here we have both a rarefaction and a shock waves propagating in front and behind the wall. But because of the shock wave, it turns out that hybrid and deflagration will behave in a very similar way, simply because the boundary conditions have a very similar structure in both cases. So in both cases, we have the velocity which is given behind the wall and the temperature in front of the shunt front. And because of that, they will behave very similarly compared to the detonation, which is completely different, as we will see. And in particular, the transition from deflagration to hybrid is done continuously, while from hybrid to detonation is discontinuous. So now that we have this type of solution, we would like to actually compute the wall velocity. So how can we do that? We need a third equation, which generally will be the equation of motion for the scalar field. So already this is much more complicated than the matching equation that we had before, simply because this is a differential equation that we need to solve everywhere inside of the wall, not just at the two boundaries. And also it depends on delta F, unlike the matching equation, because delta F inside the wall is not necessarily zero. And so we need to determine what delta F is. And to do that, we need to solve a set of Boltzmann equation. And again, this is even more complicated to solve, first because this is a partial differential equation. And it also depends on this collision operator here on the right-hand side, which is a high dimensional integral of the distribution function, which is actually nonlinear in the distribution function. And so just to evaluate it numerically, this collision operator is actually quite challenging. And so to solve this whole equation where which depends on the collision operator is even more difficult to do so. So we need quite a sophisticated method to do that. We have a few methods to do it. The first one that has been used for a couple of years consisted in expanding delta F in a Taylor series, essentially, and taking moments of the Boltzmann equation to get a system of linear equation. I also proposed a new spectral method to do that last year in a paper. And I know also that the group here in Florence have developed a method to do exactly that calculation to solve this Boltzmann equation. But in any case, it's much more complicated theoretically and numerically to do that than just solving the two matching equation that we had before. mainly because of this collision operator, which is very, very hard to compute. And also because it is nonlinear, we actually need to linearize it before in terms of delta F. Otherwise, it will be completely impossible to do so, or at least I don't know any way that we could achieve that. So yeah, this is really something that is difficult to deal with. And this is why we are interested here in the LTE approximation, the local thermal equilibrium approximation. We will see that it drastically simplifies this picture. And this allows us to get model-independent fluid equation. By that, I mean that they will depend on a very few number of parameters, only 4, in fact, and in some cases 2. So this is much more simple than what we had with the Boltzmann equation and everything that depended on all the mass variation and the collision in the plasma. So yes, the first thing, basically LTE approximation just means that we set delta F to 0 so that we have no deviation from equilibrium anywhere in the plasma. And already this is a very great simplification. We don't have to compute it with the Boltzmann equation anymore, just because we say it is 0. Then also we can show that the divergence of the energy momentum tensor, which should be 0, of course, can be written in this form here. So the first term is actually proportional to the equation of motion. And we know that this should be satisfied everywhere in the plasma, so that this term is 0. And this means that this quantity here is actually conserved, and this is the divergence of the flow of entropy in the plasma. So basically, this means that in local equilibrium, entropy is conserved. So this is not necessarily a very surprising result. It's quite often the case in fluid dynamics that we have entropy conservation when we are in equilibrium. But here it really shows that this also applies in first order phase transition. But because of this new entropy conservation, we can get a third matching equation that we can use to solve for the wall velocity. So in practice, we have kind of traded our equation of motion for a new matching equation that only means that the entropy is conserved in the plasma. So now we have 3 matching equations that we can solve for the 3 unknown quantities, and we don't need any equation of motion or any description of what's happening inside the wall. We just need to describe it, what happens on the both sides of the wall, which is much simpler than what we had to do with the whole Boltzmann equation and equation of motion before. So yes, now I also want to talk about other motivations to use this approximation. Like I said before, we will be able to get model-independent fluid equation, and this is very useful to be able to visualize much more intuitively what's happening with the wall velocity. Also, it's actually a quite good approximation. So last year in our paper, we have compared the result that we got from the whole Boltzmann equation treatment and this local thermal equilibrium approximation with the singlet scalar extension of the standard model. And in a scan of the parameter space, we only got an average of 12% difference between the 2 results. So in general, this is much better than any other approximation that we could have, except for the Boltzmann equation, and more than enough for most application also. And something nice about it also is that local thermal equilibrium always give us an upper bound on the wall velocity. So basically, when we include the deviation from equilibrium, this creates a positive amount of entropy in the plasma, and this will also create a positive pressure on the wall, which will slow it down further. So if we neglect all of these deviation from equilibrium, this means that we have the higher possible velocity that the wall could ever reach. So even if we are very far from equilibrium, we can still use this approximation just to get an upper bound on the value. So this can still be useful. Also, like I said before, this collision operator that we need to compute in the Boltzmann equation is very challenging to compute numerically, but also theoretically. In fact, we have to do that calculation to leading log accuracy, which is quite bad. In fact, there is several version of this approximation, and they give a result that differ by a factor of 2 or even more than that. So this gives you an idea of the accuracy of this collision operator, and this also means that if we solve the Boltzmann equation with this collision operator, we will have a large uncertainty on the wall velocity as well. And also, this must be linearized, and this linearization is only good when the plasma is close to local thermal equilibrium. Otherwise, this really isn't justified. So again, if we are able to use the Boltzmann equation treatment to solve for the wall velocity, this means that we have to be close to local thermal equilibrium. So in any case, this local thermal equilibrium approximation should be not too bad in that case. Yes, and now if we want to compute, like I said, model-independent fluid equation, something very useful that we can do is to fit our model to some equation of state. In general, the potential that we get for our particle physics model is a very complicated function of the temperature. But it turns out that we can approximate it very effectively by very simple equation of state. One of the most used one is the bag equation of state, where the plasma is radiation dominated, so that the speed of sound squared is 1/3, and the pressure is proportional to the temperature to the port. It turns out that we can generalize this bag equation of state to the so-called template model, which is essentially the same, but the speed of sound can be whatever you want. So here the pressure will be proportional to T to the mu or T to the nu, and mu and nu can be related to the speed of sound through these equations here. And yes, this allows us to fit our particle physics model to this very simple function, as long as the speed of sound in the plasma is approximately uniform. So yeah, basically the speed of sound cannot be a function of the temperature in that approximation. But in a lot of cases, this is a pretty reasonable approximation. So yes, the thing that is useful with these equation of state is that they depend on a very few number of parameters. And here we can actually redefine a couple of these. So first we have this theta pseudo trace in terms of the energy and the pressure in the plasma. And from that we can define this alpha parameter, which is very often used to describe the strength of the phase transition. So this is essentially the amount of vacuum energy which is released during the phase transition divided by the thermal energy in the thermal bath before the phase transition. So the larger alpha is, this means that there is more energy that will be released during the phase transition, so the stronger it will be. And finally, we have this psi parameter, which is the ratio of enthalpy on both sides of the wall. And this can be related to the ratio of effective number of degrees of freedom. And for the standard model, usually this is above 0.9, between 0.9 and 1, actually. And yes, in terms of these new parameters, alpha and psi, we can redefine, in fact, re-express the matching equation that we got before. So first thing that we can do is eliminate T minus, the temperature behind the wall, from the equation. And we get these two new algebraic equation that depends on the two plasma velocity, V plus and V minus, as well as the temperature in front of the wall through this alpha and psi parameters. But in general, it's not very useful to have alpha and psi depend on t plus because we don't know t plus beforehand. So what we can do actually is to relate these parameters to the value evaluated at the nucleation temperature with this equation here. And here we know what is Tn beforehand, so it's actually possible to compute alpha and psi at the nucleation temperature before we do this calculation. And at the end, this means that to be able to compute the wall velocity when we are in local thermal equilibrium, we only need these 4 parameters, alpha, psi, and the 2 speed of sound on both sides of the wall, all evaluated at the nucleation temperature, which is much simpler than what we had to do with the whole Boltzmann equation treatment. So now I will look at some result that I got with this approximation. So first, let's talk about detonation solution. We will see that they are a bit particular. So just a reminder that these are a supersonic solution with a rarefaction wave propagating behind the wall. And if we compute the wall velocity as a function of alpha, the strength of the phase transition, we see that we actually have a decreasing function of alpha. This is a bit surprising because alpha, like I said, is proportional to the vacuum energy that you release. And this is really this vacuum energy that drives the expansion of the bubble. So now you're telling me that if I increase the pressure on the bubble, it will actually slow down the wall. And in fact, this is a sign of an instability here. We will see in the next slide that, yes, these solutions are actually unstable. So, yes. Here, to understand that, I draw the pressure on the wall as a function of the wall velocity. And so to have a solution, to have a static solution where the wall doesn't accelerate, we need a pressure of 0. So we see that we have a solution here. And yes, this curve is actually not trivial at all. We see that there is a very large pressure peak that is actually maximized at the Jouguet velocity, at the boundary between hybrid and detonation. And after the Jouguet velocity, we see that it is decreasing. And this is because of this decreasing behavior that the detonation solution will be unstable. Basically, imagine that we have a solution here for detonation. If we go just on the left, we will have a positive pressure on the wall, which will slow it down, driving it farther from the solution. If we go on the right of this solution, we'll have a negative pressure that will accelerate the wall, driving it to the speed of light, essentially. So yes, whenever we are a little bit not on the solution, we will go farther away from it. So it is an instability. But anyway, we also see that whenever we have a detonation solution, we will also be able to find a deflagration or hybrid solution, just because the pressure, we can always find a point for hybrid or deflagration solution, which will be equal to the detonation solution because of this pressure peak, essentially. So this means that if we are in a realistic situation where the wall velocity starts with 0 speed, it will slowly accelerate until it reaches the first solution that it can reach, which will be the deflagration or hybrid one. So it will never be able to reach the detonation. So yes, basically we don't need to take into account this detonation. We will only be interested in deflagration or hybrids. And unfortunately, Unfortunately, they are a bit more complicated to deal with due to the fact that they have two boundary conditions that are not at the same point in space. So we have one in front of the shock front and one behind the wall. So we need to relate them by integrating these differential equations, which are essentially the conservation of energy momentum tensor, but here for a spherical bubble. So yes, we need to integrate this equation and relate the two boundary conditions, and then we can solve the whole system of equations. So it's a bit more complicated to do that, but at the end, it's not too hard. And this is the result that we get. So on the top plot, we see the color shows the wall velocity as a function of psi and alpha. And these are only deflagration and hybrid solution, no detonation, like I said before. And the dashed line is actually the region where the wall velocity is equal to the speed of sound. So that on the left side of this line, it's deflagration, and on the right side, it's hybrid. And we see that it's actually quite surprising. We are able to get a very fast hybrid solution at a very strong alpha factor. And this is a bit surprising because we would expect, if we look at the pressure here, if we increase alpha, you increase the pressure that drives the wall forward. So at some point, we would expect that we would be able to overcome this large pressure peak and essentially accelerate until it reaches the speed of light, essentially. But here, what we see is that it happens effectively in this region in white at the top of the plot, but it doesn't happen for smaller value psi at the bottom of the plot. So what happened essentially is that when psi is smaller, if you increase alpha, yes, you increase the pressure on the wall, but you also increase the length, or the pressure peak will become taller essentially. So it will be harder to overcome the pressure peak, and it will still be able to find a hybrid solution even if alpha is very large. And actually, we can show that below, I think, psi equals 0.77. You can have alpha as large as you want, as large as infinity, and you will still be able to find a hybrid solution. And this is very interesting for a few reasons. The main one is for baryogenesis. So to do baryogenesis, you absolutely need to have either a hybrid solution or deflagration. You cannot do it with detonation, or at least it's much more difficult to do that. And this means that this whole region, we would be able to get a hybrid solution, which would be very strong, and this would be able to produce a very strong signal of baryon symmetry. So yes, for baryogenesis, this region is very interesting. And another interesting fact here is that even if we're not in local thermal equilibrium, we would still expect to find a hybrid solution here, simply because, like I said before, LTE gives us an upper bound on the wall velocity. So if you include deviation from equilibrium, the wall velocity in this region will just be smaller. And again, it will still be a hybrid or a deflagration solution. Yes, I think this is very interesting to see that in any case, even if you have very large deviation from equilibrium, you can have hybrid walls as strong as you want, effectively, as long as psi here is low enough. And yeah, also I show on the bottom plot the relation between the wall velocity and the two speed of sound. So I vary mu and u from 4 and 5, which correspond to a speed of sound between 0.5 and 0.58 roughly. And here we see that the dependence is much milder than on alpha and psi. It's about 10% that we get. Yes. Yes, I just wanted to talk a bit about the range of alpha that is allowed to get a deflagration or a hybrid solution. So we see here that there are basically two regions where we cannot find any solution. On the left-hand side, it's simply that if we go there, the difference of potential energy between the two minima doesn't have the right sign. So in that case, no nucleation can ever happen, just because we are already in the true vacuum. So this is not a surprise to see that we don't have any solution below that value of alpha. And yes, like I mentioned before, we also have a maximum value of alpha, which is reached when we are at the top of this pressure peak. But actually, as we see here, this maximum value of alpha actually diverges at a value of 0.77. And so, like I said, this is very interesting if we want to do baryogenesis or stuff like that. And finally, I just wanted to talk about the spectrum of gravitational waves that we can get also from that. So here, a very important quantity is the kinetic energy fraction, which is essentially the ratio of kinetic energy that will be produced during the phase transition. And to get large amount of gravitational wave, we need this K to be as large as possible. And again, we see that to get a high K, we need a high alpha, so a very strong phase transition. This is, again, not very surprising. But this shows that in this region, again, where psi is quite small and alpha is very large, we would be able to get very strong gravitational wave as well as baryogenesis, something that we were not able to do in the singlet scalar extension. So this is really a region that would be quite interesting to look at in the future. So yes, that's pretty much what I had to talk about today. So if you have any question, of course, I will be happy to answer. And thank you for listening. Yeah.
Okay, so can I ask you two questions?
Yeah, sure.
One question is that you evaluate the alpha parameter at the nucleation temperature, right?
Yeah.
What if there is a hierarchy between percolation and nucleation? Does it change a lot, your results?
Oh, yeah, right. Yeah, actually, it depends what you're interested in. Yes, if you want to compute a gravitational wave, yeah, the relevant temperature would be the percolation temperature. Yeah, that's right. So you would just have to replace Tn by Tp in that case. But for baryogenesis, I think the nucleation temperature would be more useful in that case. So yeah, it's just a matter of what you're trying to compute, and in that case, you can choose either of the two. Yeah.
But I mean, for the wall speed, it doesn't change a lot, right, for your computation?
Well, yeah, I wouldn't. No, in fact, you're right. Yeah, actually, it doesn't. When you do the actual calculation, it doesn't depend on the nucleation temperature at all. It just factors out all the equation. So it will depend on all the thermodynamic quantities, like the ratio of effective number of degrees of freedom or the strength of the phase transition. So as long as these quantities doesn't change too much, you will get the same result. Yeah.
And for the second question, so you did the scalar singlet extension of the standard model,
Yeah.
right? So this, I think, for the old method of computing the wall velocity, this was also done for baryogenesis. And you said you got 12% difference, right?
Yeah.
Does it change anything for the viability of baryogenesis in this case, or no?
I haven't looked at that, but I would guess that it wouldn't change too much. Like I said, to do baryogenesis, you really need either hybrid or deflagration. So as long as you're able to get that, you should be okay. Yeah. Mm-hmm.
Thank you.
Yeah.
So to perform this computation of the velocity, you are neglecting the contribution from out of equilibrium, the formation of the distributions of the plasma, right? Can you comment on this and give an estimate of how much this contribution could be?
Neglecting the contribution from
delta F.
sorry?
You're putting delta F equals 0, right?
Yeah. Yeah, like I said, in the singlet scalar extension, it's about a 12% error on the wall velocity by setting delta F to 0. It's an average. Sometimes it's larger than that, sometimes smaller. But yeah, in most cases, 12% is more accuracy that you actually need. So yeah.
It's 12% on the final velocity. On what?
It's a 12% error on the wall velocity. So
Okay.
it's basically the difference of the two results divided by the average of the two results.
Hi, can you hear me?
I don't see questions on the web. Angel is speaking. We cannot hear.
Can you hear me?
We cannot hear him. Please, Angel, write it in the chat because we cannot hear. Non sentiamo. Okay, wait, maybe there is a technical problem. Wait a moment. Angel, maybe you are muted.
Now, can you hear me now?
Oh, yes. Okay.
Okay. No, so thank you for the talk. It was really nice, but I was curious about these cases that you mentioned that are like super fast hybrid cases, no? And it was just, I wanted to ask you, in that case, if you have a super fast hybrid wall, it means that you have an even faster shock wave in front of the bubble, no? And that shock front is also perturbing the plasma. So maybe in those super extreme case, neglecting delta F is a bit too much for an approximation. I mean, if you could comment a bit in this, I would be thankful.
So you're asking if that superheated shock front will create more deviation from equilibrium? Am I understanding?
Exactly. Yeah, that's what I was thinking. If it's too fast, then the bubble wall itself is finding a plasma which is.
Yeah, that's true. That if we have a very large variation of temperature at the shock front, that could drive the plasma out of equilibrium in theory. But yes, like I said, this discussion for very fast hybrid wall, actually, I don't expect the LT approximation to be very good when the wall velocity is that high, even for a hybrid solution. But like I said, we will still get a hybrid solution because LT always gives you a lower bound, an upper bound on the wall velocity. So in that case, I think this is the most interesting conclusion that we can have. Of course, if the phase transition is very strong, deviation from equilibrium will become larger, and at some point LTE is not necessarily a good approximation. But even if that's the case, that only means that the wall velocity will be smaller than what we predict here, and it will still remain a hybrid or deflagration. And that's the main thing that I wanted to show here. Yeah.
Okay, thank you. And if you don't mind, I have another question. So thank you for the answer before. And so when solving the Boltzmann equation, when one considers also local equilibrium, so you have a profile for the temperature and the velocity, the shape itself of the temperature and the velocity profile is important. So you have terms proportional to the derivative of the temperature and the derivative of the velocity. I would just wanted to know, in this method that you presented today, is also the shape of the of the temperature and velocity of the plasma profiles important, or you just need the values at, let's say, plus infinity and minus infinity, and that's it?
Sorry, I'm not sure I understood correctly. Can you repeat, or?
Yeah, sorry. So no, I was saying that when solving the Boltzmann equation, if one wants to solve the delta F term, it's important to know not only the temperature of the plasma at infinity, let's say much more in front of the wall and much behind the wall, but also the shape that the temperature profile has, the shape that this function has. I just wanted to know if in your method you also need to know the value of the temperature of the plasma at every position across the bubble.
Sorry, I'm still having a hard time hearing. Does somebody understand? Or?
I guess that the answer, the question that is making is the following. When you solve the Boltzmann equation in the source term, you have also the derivative with respect to Z of the temperature profile and the velocity profile. I guess that what Angel is asking you is if in this region the profiles have an impact or not. Is this correct, Angel?
Yeah, if for him these profiles are important or not, the shape itself.
Yeah, again, this is something we haven't looked at, but in principle, yes, it can have an effect. Yes. So even if we have a large temperature or plasma velocity variation, yes, that can drive the plasma out of equilibrium because of that. But like I said, in that last part of the talk, where I'm interested at the very strong phase transition, the important thing that we can derive is really that they will be hybrid or deflagration. Even if they are very strong, we will still be able to get this type of solution, which is something that wasn't expected at the beginning. Yeah. But yes, in principle, these things are important, the variation of temperature and plasma velocity to determine the deviation from equilibrium. Yeah.
Okay, thank you very much. Thank you very much for the talk again.
Yeah, thanks. Yeah.
I have another question. So in the singlet extension of the standard model, if I understand correctly, in the first plot, basically we are focusing on the very top left corner. Okay.
Yeah, this is above 0.9 for the singlet scale.
Yeah. If I remember the number, they are basically there. My question is, are there any models that actually predict?
Actually, I think there are a few. I'm not an expert in that. My collaborator Yohinde is a bit more. Knows a bit more about that, but I think in some, if you have a dark sector and you have some phase transition happening in that dark sector, you could have such a small value of psi, or maybe some other exotic model that I don't know about. But yeah, it's definitely something that isn't trivial to get, because in the standard model we don't have such a large variation of degrees of freedom. But yes, in principle, this is possible.
You were mentioning for psi, but what about alpha instead in that model? Do you actually satisfy the bound that you found for alpha?
Yeah, alpha is a bit easier to deal with. Yes, it's possible to find models where alpha can just be adjusted with a parameter. So yeah, I remember I worked in a SUSY breaking phase transition, and we could get alpha very high in that kind of phase transition. But yeah, it depends on what model you're working with.
And another question that just came in my mind, do you have an estimate also of the change of the temperature across the bubble wall in that region, that particular region where you have very strong alpha and very, let's say, psi small?
Yeah, for that region, it can be quite high. It depends on the precise value of alpha, of course, but it can be 2 or even 10 times larger if we have a very large alpha. But in general, in the standard model, above 0.9 here, it's about 10%, the difference. But yeah, it can be very large when alpha becomes larger. Yeah.
Okay, thank you.
I don't see any other section on.
Yeah. Thank you.
Bye to everyone.
Yeah.